The intermolecular forces we mentioned in the previous section affect the boiling point, as we were talking about previously, and they also give rise to cohesive forces and adhesive forces. Cohesive forces are the attraction of the substance to itself, and adhesive forces are the attraction of the substance to another substance. So in your textbook, they have a little picture of a glass tube with water. You can see the meniscus like this because the water's attraction to the glass is stronger than the attraction to itself. In contrast, when you have mercury metal, the meniscus is actually inverted because the cohesive forces of mercury to itself are stronger than the adhesive forces to the glass. Water, however, is very strongly attracted to glass, and if you put a glass tube into a cup of water, some of the water will actually get drawn up into that glass tube. And if you have a thinner glass tube, the thinner the glass tube, the higher it's actually going to draw up. So here I've shown a thinner tube and the water's gotten drawn up even higher into the tube. The height of the water that's drawn up into the tube can be calculated. It has all these factors going into it. The surface tension of the fluid, so it doesn't have to be water, but the surface tension of the fluid, the angle of contact, the radius, as I mentioned, this radius is in the denominator, so the smaller radius will have a higher height of the fluid drawn up into it. We have the density, symbolized by the Greek letter rho, and then we have gravity. So let's see if we can put all these into action and figure out how high water will get drawn up into a glass tube that has an inner diameter of 0.320 millimeters. So this is a very thin tube that we're talking about here. Remember that the radius is half the diameter. The radius would be 0.160 millimeters for this tube. Alright, so for the height of the water, it's going to be 2 times the surface tension, which is given to us here. It's 0.07199 kilograms per second squared. Then the angle of surface contact between water and glass is 0. The cosine of an angle 0 would be 1. So this cosine of theta is 1. So for the radius, I have this in millimeters. I can see that we have a bunch of meters that are going to be at in the other units of this equation. So I'm going to go ahead and convert this 0.160 millimeters to meters, and I'm going to say that it's 1.60 times 10 to the negative 4 meters. So there we have the radius. The density is 1,000 kilograms per meter cubed, and then the force of gravity is 9.81 meters per second squared. So let's check on our units here. Our kilograms are going to cancel. We have 2 meters in the denominator, 3 in the numerator. So I'll just cross out the 3 here. That'll cancel 2 of these. We'll still have meters. And the second squared are going to cancel. So that is all we're going to have is meters. So this ends up being 0.0917 meters, which is about 9 centimeters, about 3.5 inches. So it's a significant height that it gets drawn up into this very thin glass tube. All right, this second problem is a little bit different because we are not given all these different constants like the surface tension and the angle of surface contact. We're not even given the density of this certain fluid that we are told about. We're just given the height and the thickness of the first glass tube, and then the thickness of a second glass tube, and we want to know the height of that second set of conditions. So the things that are changing here are the height. We have a different height and we have a different radius of the tube. The surface tension, even though we're not told what the fluid is and what the surface tension is, if we're using the same fluid, it has the same surface tension. The angle, even though we're not told what it is going to be the same as well. And the density and the gravity. So all of these are going to be the same for both of these situations. So the surface tension, the angle, the density, and gravity, all of these are going to be the same. These are going to be constant. If we multiply both sides of this equation by r, we get h times r on one side, and everything on the other side is a constant. They're all things that we don't know, but none of them are changing. So the height times the radius is going to be the same number for both of these scenarios. So the first scenario, the height times the radius, is going to equal the second scenario's height times the radius, because the height times the radius is not going to change in this situation when we haven't changed the fluid. So the first scenario has a height of 3.46 centimeters with a radius of 0.250 millimeters over 2, because this is the diameter. So it's 0.125 millimeters. And then the H2 is what we don't know, and the R2 is 0.380 millimeters over 2, which is 0.190 millimeters. So this problem becomes even simpler to set up. So now we have a setup that's very similar to Boyle's law or something like that, where we have one set of conditions and the second set of conditions. And then we can just divide both sides of the equation by the 0.190 millimeters. And then this will cancel. The millimeters will cancel on this side. And H2 would be 2.28 centimeters. And this makes sense because the second tube is a little bit wider, and so the height of the column of fluid is not going to be as high. And so if you are keeping the material of your tube and your fluid the same, and you have a beginning set of conditions and an ending set of conditions, then you can just use this H1R1 equals H2R2, which is a fairly simple equation to use.